But here's the catch. Our ability to really use these types of quantum materials effectively lies in being able to get as much light as possible out of the crystal.
The really exciting part is that we can use silicon. The silicon is opaque at this red light, so it's not obvious that we can use this for NV center in the diamond. But in the nanoscale, which is our design, then the light can come channels into the silicon antenna and then go into the free space.
And I think we can readily adapt the types of antennas that Minjeong developed and demonstrated to those color centers, and that opens up a lot of opportunities in sensing and a lot of different modalities.
I'll start by talking about clouds of atoms, which are kind of workhorses of quantum technologies, from being able to allow us to measure very, very small changes in magnetic fields and pick up small RF signals to being able to keep time in the most accurate way possible. Atoms are also being used to build quantum networks and next-generation quantum computers. An alternative quantum material is one where we create artificial atoms, basically analogs of trapped atoms or ions in crystals such as diamond. But unlike with some of the apparatus that you see in an atomic physics lab, you actually do not need a lot of lasers, really just one that can allow you to excite the emitters and extract fluorescence light out of it. And you do not need cryogenics, and nor do you need any vacuum hardware. But here's the catch. Our ability to really use these types of quantum materials effectively lies in being able to get as much light as possible out of the crystal. And light, when they're emitted from these quantum emitters inside the diamond crystal, they tend to be trapped. So our work is focused on making new types of optics that can allow us to efficiently extract light while maintaining the quantum properties of the emitter.
Previously, most of the people carve into the diamond itself, which is the hardest material in the world. So it's like hard to etch down, and also while doing the carving it down, that it can damage the surface of the diamond. So it can degrade the NV center and also change the surface chemistry. We came up with a new kind of invention, which is optical antenna made out of crystalline silicon. The difference of our approach is that we are putting the silicon membrane out of SOI wafer, so that we are having silicon membrane on top of the diamond and then making an antenna there, and also protecting the diamond surface at the same time. And also silicon has a much more higher refractive index compared to the diamond, so that light can efficiently get out rather than trapped inside the diamond. The reason why we're calling this as antenna is that we can get the more light out from the NV center in the diamond and then redirect the light in the free space. But silicon here is the most widespread material that current industry are using. So all the electronics now have silicon inside. So which means that we can scale up this invention and it can be used directly in the industry.
On the licensing and commercialization side, we're really excited about the possibility of using this invention to improve quantum sensors, to essentially improve the signal to noise in a magnetometer that might be used for a navigation system or could even be used for some sort of biomedical application. We're certainly open to working with companies, but we also have our own effort in commercialization that is in the process of spinning out, and really already has spun out of the university and out of my research group and Professor Jennifer Choi's research group. The academic plan is to collaborate with other researchers, especially ones in the region where we have an incredibly strong quantum community. We're fortunate to have an amazing quantum information science community at the University of Wisconsin-Madison and in the upper Midwest. And so we think that we as an optics research group can design optical components, can design optical metasurfaces, can design new types of antennas that help interface with quantum mechanical objects, and that should enhance applications not only in quantum sensing, but also quantum networking, quantum computing, and others across quantum information science.
Hi, I'm Emily Bauer, Director of Licensing with WRF. If you like what you've heard and want to learn more about this high potential technology, please get in touch using the information on your screen and in the description below. And don't forget to subscribe for more great videos from WRF.